Hi folks, I wanted to make a video of practice problems number 3 from Apologia Chemistry, just so we have enough class time to cover all the other topics. So we covered 2 in class last week. Practice problem 3 is pretty similar, but I just want to make sure that we cover it together because these problems have many steps. So, problem 3 reads, a chemist does a reaction rate analysis of the following reaction. And it's this, which here's the name of this chemical, 11122 pentachloro 2 1122 tetrachloroethoxyethane. This is a very toxic and terrible, monstrously named chemical. And of course, you don't have to know that. I had to look it up, and then I had to ask my friends when I couldn't figure it out even after I looked it up. So, very unusual chemical I've never come across before. But anyhow, it reacts with fluorine ions and gives us C4Cl9F plus hydroxide ions. So we want to find the rate reaction for this. And as you remember from last week, this is a very multi-step process. So I'm going to erase this so we can fit all 5 steps of this on the board. So here we go. First thing we want to do is just write the rate equation with what we know already filled in. So we know that the rate is equal to a constant K, and don't forget, even though you can't see it in this equation, K considers temperature. So we all know that reaction rate usually increases as temperature increases. And even though in the rate equation you don't see that, you know that K is the factor where temperature is considered in the rate equation. So we've got K here, and then the concentration, that's what these brackets mean, concentration of that chemical with the massive name. And we don't know what the order of reaction with respect to that chemical is, so we're going to call that X for now. And the concentration of fluorine ions, and we also don't know what order it is with respect to fluorine ions yet, so that's a Y. We've written everything we know. Second thing we're going to do is we're going to look at what happens when one chemical's concentration is constant and the other changes. So if we say compare let's see, if we look at trials 1, 2, and 3, looks like the concentration of, between trial 1 and trial 2, concentration of this C4Cl9OH is constant. The concentration of the fluorine ions doubles. So between trial 1 and trial 3, trial 2, the concentration of C4Cl9OH is constant, so we're not worried about it. And concentration of fluorine ions doubles. Okay, so when concentration of fluorine ions doubles, what happens to the rate? Well, if you look at the rate between trial 1 and trial 2, it's exactly the same. Rate stays the same. That says same, I promise. Same. Okay, well, if rate stays the same when concentration of something doubles, what does that mean? Well, what it means is that Y here, the exponent that tells us the order of reaction with respect to fluorine, is 0. So that tells us Y equals 0. Rate doesn't change no matter what you do to the concentration of fluorine, as long as there's some to react. We can dump in tons and tons of fluorine and not actually increase the rate of reaction, even though, according to the kinetic theory of matter, increasing the concentration of reactant should increase rate. This is one of those weird times that that doesn't happen, and that's too complicated for you to understand why at this point, but outside of the scope of the class. But it's true that in the case of this fluorine ion, increasing the amount doesn't increase the rate of reaction. So then we'll compare trial 1 and trial 3. Between trial 1 and trial 3, we see that the concentration of both reactants actually doubles. And we know that the concentration of fluorine doesn't matter, because if it's the only thing that changes, the rate doesn't change anyway. So we're going to just worry about the concentration of the C4Cl9OH, and it doubles here between trials 1 and 3. Okay, so if the concentration of that doubles, what happens to the rate? Well, if we look at our rate data, in trial 1, the rate is 0.0202, and that's in molarity per second. In trial 3, it's 0.0404 molarity per second. So it looks like the rate doubled. So when concentration of that monster doubles, the rate doubles. Okay, so we just say, well, in that case, X is going to be what happened to the concentration divided by what happened to the rate. So that's going to be first order with respect to this reactant, the C4Cl9OH. A first order, that means X equals 1. And just as an aside, overall order of reaction means that you just add up all of the exponents associated with the reactants. So we have 2 reactants, so we'll have 2 exponents. It's 0 order with respect to this one, first order with respect to this one. So the overall order of reaction is 1, because 0 plus 1 is 1. Then we just have to plug in. You can choose any of the 3 trials. It looks like I chose trial 1, apparently. Yes, trial 1. Okay, so fourth step is to plug in to find K, the rate constant. So it looks like in trial 1, the rate is 0.202 molarity per second. So we know R equals K, which is what we're trying to find, times the concentration of excuse me, C4Cl9OH, which in trial 1 is 0.25 molar. And we know that with respect to that, our exponent is 1. And then the concentration of fluorine, which in this case is also 0.25 molar, raised to the 0 power, because we found Y to be 0. Well, that just makes it 1. Anything raised to the 0 power, of course, is 1. So multiplying by 1, of course, does nothing. So we just work out this, solve for K. So we have 0.202 molar per second divided by 0.25 molar. K is going to be equal to excuse me, 0.081, 2 significant figures. When you divide molarity per second by molarity, the molarities cancel out, so you just get 1/2 for your unit in this particular equation. But remember, K can have different units depending on the order of reaction. So don't panic if you have a test question where you don't have this unit for K. You can have, 1 over molarity squared times seconds, or any strange thing like that. So make sure you keep your units straight on every problem, because every K has different units. Okay, so our last step is to write the rate equation. No problem is complete until you do this. So we found rate, we're just plugging back into this first equation, to be equal to this K, 0.081 1/2, times the concentration of C4Cl9OH raised to the first power. And that's actually it. We don't even need to include the fluorine ion because it's zero order with respect to the fluorine ion. So it does not affect the rate at all. So this is our rate equation. R equals 0.0811 over second times the concentration of C4Cl9OH raised to the first power. And I guess that wraps up that problem. I'll see you in class tomorrow.